Now, let's look at how we find the area of a regular polygon. In front of us we have a pentagon, but the rules we're going to talk about apply to all polygons. That includes triangles and squares. They can be regular and they follow these same rules and same formulas. Now, for those that like to start with a formula, we can write down the formula for a regular pentagon or any other polygon. It's a pretty easy formula. The formula is 1/2 AP. Now, in that formula, A refers to the apothem. I know, what's the apothem? In my regular polygon, I have a point which represents the center. If I were to draw all of the diagonals in this regular figure, they're all going to meet somewhere. That's the center of the figure. The vertical line, or the perpendicular line, that connects the apothem to a side, the center to a side. So center, side. This piece right here, this guy, is called the apothem. Now, a pentagon actually has 5 apothems I can draw. The key is that they have to hit the side at a right angle, and we're going to use that right angle as part of our work today. Now, the P in the formula refers to the perimeter of the figure. Now, perimeter is not a real tough one. We've done that one before. That's the distance all the way around. In this particular case, I have a pentagon with sides each being 8 units in length. I'm going to put units on there to make it easier to talk about. We'll call it centimeters. So if each of these sides is 8 centimeters, and I'm talking about a pentagon, that means I'm talking about 5 sides that are all the same. Regular, 5, means each of these sides is 8 units in length. My perimeter, therefore, 8 times 1, 2, 3, 4, 5 puts me at 40 centimeters in perimeter. The nice thing with working with regular figures is all the sides are the same, which is why a square counts. All 4 sides of a square are the same. So it's a regular quadrilateral. I can also do an equilateral triangle. It gets the classification of regular. There's one more bit of vocab we're going to need. I want to draw this triangle. Notice, these are not apothems. They connect the center to a vertex. That's different. Remember, the apothem comes down and hits at a right angle. These hit at the vertex. This angle right here is called the central angle. We're going to use that in our work. Now, the good news, based on the number of sides, that central angle is consistent. So no matter how big I shrink or stretch this pentagon out, the central angle will be the same, because there are 5 central angles in that figure. So I'm taking that 360 all the way around. So 360 all the way around, dividing it by the fact that I have 5 of those central angles, and each one is going to have to be 72 degrees. Now, if this had been a hexagon, there's my center. That would be an apothem. This would mark off that central angle. There are 6 of those going around. So 360 divided by those 6 would put me at 60 degrees each. So basically you take 360 divided by the number of sides, and that will always tell you how big that central angle is. Quick recap. Formula for the area of any regular polygon is going to be 1/2 apothem times perimeter. This particular pentagon we're working with has a side 8 centimeters. This dotted line here represents the apothem. It runs from the center to a side where it hits at a right angle. And then this angle is my central angle. It represents the top of a triangle formed by connecting the center to two vertices that are connected to the same side. So I have that triangle right there. Now, there's some more stuff that I already know from what we've done that I can apply here. For example, since these lengths are going to be the same, I know this piece down here is broken in half. That's a perpendicular bisector. That comes from our rules with isosceles triangles. It also tells me that this angle is bisected. That also comes from rules with isosceles triangles, or I could perhaps look at some other rules of triangle congruency. Or, at this stage, you could take me at my word that the apothem bisects that angle. Now, as we've just said a few moments ago, this angle here is 72 degrees. Where did I get that? Remember, I got that by taking 360, dividing by the 5 angles, which gives me 72 for that one angle. I'm going to pull this triangle out. Let's redraw it over here so I don't have all that pentagon stuff happening. So that's 72. That makes a right angle. It also cuts the bottom in half. The full size is 8, which means if I break it into 2 parts, each one is 4. Why am I doing this? My goal is to calculate the area. That's what I want to do with these problems. Come up with the area of this figure. I can't get the area unless I know how big this apothem is. So my goal is to find that height, this apothem. You could call it a type of altitude. I can then use that in the formula to calculate the area. Perimeter, that guy's pretty easy to get. So what I'm going to do is I'm going to continue to look for things I already know how to handle. For example, since this angle is bisected, if the whole angle is 72, that angle is going to be 36, half of 72. This angle over here is also going to be 36. I know how to work with right triangles. We've spent a great deal of time working with right triangles. Again, I'm going to pull that triangle out so I can focus on it. The apothem is what I want to come up with. So I'll make a note that I'm looking for that apothem. That's a right angle. That's 4. Again, that's this distance right from here, moved over to here. This angle, 36 degrees. Now, if you kind of track this back up, this triangle came out of here. This triangle came out of here. And again, I'm still trying to stay within the realm of the rules that we've practiced. Now, I know how to get this distance here. We've done those. That goes back to our days of doing sine, cosine, and tangent. For example, I know that the tangent of an angle is the opposite divided by the adjacent. When I look at this triangle here, I can see that the opposite of my angle, the opposite side is going to be 4. The angle in question is going to be 36 degrees. I can now calculate that apothem. So I can say the tangent of 36 degrees is going to equal 4 over A. Now I go to my calculator because I don't have tangent of 36 memorized. And let's get some math happening here. So tangent of 36 gives me 0.726 is 4 over A. I'm going to write this as over 1 so that it's a proportion I can solve. I cross multiply. That's going to give me 4. I'll write over here. 4 times 1 equals 0.726A. To get the A by itself, I'm going to divide. And that gets me an answer. The apothem is going to equal Let's find out what it does equal. 4 divided by 0.726 gives me an answer of 5.5. I have my apothem now. This distance right here is 5.5 centimeters. Now, it's a lot of work to get that height, but I need it if I'm going to calculate the area, because the area is based on the length of the apothem times the perimeter times 1/2. The good news, I'm going to be using tangent. I'm going to be using angles I can easily calculate by thinking about how many sides there are, and I'm going to be working with half of one of those sides as part of my work. Now that I've got my apothem, I can finish the problem out and calculate the area. Some problems will provide you the length of a side and the apothem, but they don't have to, because there's a connection between that side of 8 centimeters and this apothem of 5.5 centimeters, which represents all the work we just completed using the tangent. Going to my formula, I just have to plug everybody in. So area is 1/2 the apothem, 5.5 centimeters, times the perimeter. In this case, I know that's 40. Now that 40 comes from 8 centimeters per side times 5 sides. And the 5 comes from the fact that it's a pentagon. Pentagons have 5 sides. So then I can run that through the calculator. I take my 5.5 times 1/2 times 40. And that's going to get me an answer in the ballpark of 110 square centimeters. Now your answer might be, my calculator reads 110.11, so we might be off a little bit based on how much we rounded in our calculation of apothem. So you are allowed a little discrepancy. As a small caution, you may also see formulas online that look very similar to this, but they don't say perimeter. Something along those lines, where it says 1/2 ASN. And in this case, N represents the number of sides, S represents the length of one side, and again, the half and the A go to the half and the apothem. This is basically their way of writing the perimeter. So as you're studying other resources, you may see that formula as well. It's the same formula we're using. So remember with these, my area formula for any regular figure, any regular polygon, so it has to be regular, 1/2 apothem perimeter. And most of your work is going to go into calculating that apothem unless it's provided. The apothem is the distance that goes from the center of the figure, hits at a right angle to one of the sides.